In this video, we want to continue on with our discussion of the cross product. So up here at the top, I've already written out the definition of our cross product of some vectors A and B, where A is the vector A1, A2, A3, and B is the vector B1, B2, B3. And again, that was the vector A2, B3 minus A3, B2, comma, negative the quantity A1, B3 minus A3, B1, comma, A1, B2 minus A2, B1. And so that was our cross product. What I would like you to do now is to pause this video and calculate a couple of things. I'd like you to calculate A, the vector A, dotted with A cross B. And let's do the vector B dotted with A cross B. And do that with these symbols here. So don't plug in any numbers for that. Just do that with these symbols here, remembering that the vector A is A1, A2, A3, and the vector B is B1, B2, B3. So go ahead and pause this video and do that calculation real quick. All right, I assume you have paused that video and done that calculation. And if you've done that, what you will see is that this is the scalar 0, and this is the scalar 0. So what we find is that A and B, so the vector A and the cross product A cross B, those are orthogonal to each other, right? If we have two non-zero vectors and their dot product is 0, that means they are orthogonal to each other. And similarly, B is orthogonal to A cross B as well. So what does that tell us? Well, if we have a vector A and we have a vector B, then their cross product is orthogonal to both. So that is supposed to be square, just to show that that is orthogonal. So this vector up here is A cross B. It is orthogonal to both A and B. And in fact, which direction does it point in? Well, that direction depends on the right-hand rule. So if you use the right-hand rule that we had done when we were drawing out our coordinate system for the three-dimensional coordinate system, so the direction of X, Y, and Z axes, if you do that same right-hand rule, your fingers will curl in towards A, so the first part of the cross product. Your arm will point towards B, so the second part of the cross product, and your thumb will always point in the direction of the vector that is the cross product of A and B. So that is a geometric interpretation of what the cross product does. Okay, so let's clear that out and talk about these properties of the cross product. We've already mentioned the first property here at the end of the second video, that A cross B is the same as the negative of B cross A. So the cross product is not commutative, i.e. A cross B is not equal to B cross A, but they are the negatives of each other. The second property is what we just talked about at the first part of this video. Assuming that A and B are non-zero vectors themselves, then the cross product of those two vectors is orthogonal to both A and B. And moreover, the direction of A and B is given by the right-hand rule. The third property here is I cross J is equal to the vector, the standard unit basis vector K. Which if you apply that right-hand rule on that, you should be pretty clear that that is the case. And applying the first part of the first property up here, if I cross J is K, then J cross I is negative K. right? J cross K is I, so K cross J is negative I, and K cross I is J, so I cross K is negative J. And we can get 6 relationships there between I, J, and K. Moreover, let's look at property 4. Property 4 says that the angle theta is the angle, if theta is the angle between A and B, then the magnitude of the cross product of A cross B is just equal to the magnitude of A times the magnitude of B sine theta. And in particular, that means that the cross product of A and B is 0 if and only if either A is 0, B is 0, or A is parallel to B. Why would that be the case? Well, if A is parallel to B, that means the angle between them is either 0 or pi. But if the angle between them is 0 or pi, notice that the sine of 0 and the sine of pi is both 0. So the magnitude of A times the magnitude of B times 0 is 0, which tells us that the magnitude of the cross product of A and B is 0. If the magnitude of a vector is 0, that means that vector is 0. So we get that if it was A and B were parallel, or if A was the 0 vector or B was the 0 vector, then this left-hand side would be 0, which would imply that A cross B is the 0 vector. And of course, if we start with the left-hand side, that magnitude being 0, if we start with A cross B being the 0 vector, then of course the magnitude is equal to 0, which implies that either A is 0 or B is 0, or A and B are parallel because sine of theta is 0. All right, I'm not going to prove this. I'm not going to prove this equation here. You can find that video, a video proving that anywhere you wish. If you just Google that, that is an easy thing to find. So I'm going to skip trying to prove that right now, but we can use that to talk about why the magnitude of the cross product is the area of the parallelogram determined by A and B. So I'm going to draw a picture here. Let's draw a parallelogram with a vector A here and a vector B here. Then the parallelogram will look like this, where again, this is another copy of the vector A and this is another copy of the vector B here. Well, what is the area of that parallelogram? The area of that parallelogram is the length of the base, so the length of vector A, times the height here. But what is that height? Well, if this is theta, right, the angle between vectors A and B, then the height here of this triangle, this is a right triangle, so the height of the parallelogram is the length of B, so the magnitude of B, times sine theta. Okay. Well, what does that tell us? This tells us then that the area of the parallelogram is the magnitude of A, which is the length of A, times the length of B, which is the length of that hypotenuse of the triangle here, right? So times the length of B, times sine theta. So that is the area of the parallelogram. Well, based on this previous property 4, this is exactly equal to the the magnitude of the cross product of A and B. So the magnitude of the cross product of A and B is the area of the parallelogram determined by A and B, which is neat. All right, we got two examples left that we want to do in this video. So let's start with this first one. Oops, there we go. Find the non-zero vector orthogonal to the plane through the points. P is 0, 0, negative 3, Q is 4, 2, 0, and R is 3, 3, 1. So to find a non-zero vector orthogonal to the plane through those points. So we have some plane that those 3 points are in. Notice that if we can find two vectors that are not collinear in that plane, then we can take the cross product of those two vectors, and that vector, that new vector, that cross product, is orthogonal to both of the two vectors that we were using in the cross product, right? That was our property 2 up above, which will give us exactly what we want. So if the point P and Q is in a plane, then the vector PQ is also in that plane. So what is the vector PQ? Well, that is 4 minus 0 in the first coordinate, 2 minus 0 in the second coordinate, and 0 minus negative 3 in the third coordinate. So this is the vector 4, 2, 3. We also have the vector PR. Oops, PR is what I meant to write there. We also have the vector PR. So this is 3 minus 0, 3 minus 0, 1 minus negative 3. So this is the vector 3, 3, 4. Okay. So these two vectors are not parallel. So when we take the cross product of those, which, by the way, for clarification, PQ is in the plane that houses the points PQ and R, and PR is in the plane that houses the points PQ and R. So if we know that those two vectors are not parallel, which they aren't because they are not a scalar multiple of each other, if they're not parallel, then we will find a non-zero vector that is orthogonal to both of these if we take the cross product of those two vectors. So that's what we want to do now. We have the vector 4, 2, 3. And we want to cross this with the vector 3, 3, 4. So let's do that. Well, to do this cross product, this is I, J, K. Then we put a 4, 2, 3 here and a 3, 3, 4. Okay, so this is equal to the vector. First coordinate is 2 times 4 minus 3 times 3. Second coordinate is negative of 4 times 4 minus 3 times 3. And the third coordinate is 4 times 3 minus 3 times 2. And we combine all of that, we get 8 minus 9 is negative 1. Then we get 16 minus 9 is 7, but we have negative of that, so that is a negative 7. Then we have 12 minus 6 is 6. So we get the vector negative 1, negative 7, 6. So we have calculated a non-zero vector orthogonal to the plane through 3 particular points. Again, how did we do that? Well, if we have 3 points in a plane that are not all collinear, so we can find 2 vectors that are not parallel. And if we have 2 vectors that are not parallel, that are in the plane, we just take the cross product of those 2 vectors and we get a vector that is orthogonal to the plane. All right. let's move on and find the area of the triangle with vertices P, Q, and R. Well, let's write out the picture of what's going on here. So if we have P here, we have Q here, and R over here. Then what we notice is we have a parallelogram that looks like that, and we want to know the area of the triangle PQR, so the area of this region in here. Notice from looking at the picture, that is half of the area of this parallelogram. Okay, so how do we calculate the area of the parallelogram? Well, recall that the area of the parallelogram is the magnitude of A crossed with B. But what is B? B is the vector PQ. A is the vector PR. So we can do the magnitude of A cross B. And I actually messed up a little bit here. I meant to do PQ as A and PR as the vector B, because that's what we did in the last problem. But notice that in the last problem, the vector PR cross, the vector PQ cross PR was -1, -7, 6. That's what we calculated in this last problem. So the vector cross product of A cross B here, which is actually PR cross PQ, now we just reverse the order. This tells us that the vector A cross B is negative of -1, -7, 6. So this is really the magnitude of the vector 1, 7, -6. Okay, and again, how do we know that, right? A cross B. We actually did B cross A in the previous problem with how B and A are defined here. So we already calculated that as -1, -7, 6. So A cross B is just the negative of that, right? If we reverse our order of the cross product here, then we just get the negative of that original vector. Okay. So we want the magnitude of this vector here. So we want the magnitude of 1, 7, -6. All right, that is the square root of 1 squared plus 7 squared plus -6 squared. All right, this is the square root of 1 plus 49 plus 36, which is equal to the square root of 86. And if we go back, we recall that the area of the triangle is half of the area of the parallelogram. We just calculated the area of the parallelogram here. So the area of the triangle is root 86 over 2. It's half of what we just calculated. And that is it for this example and this video. And this ends our lecture on the cross product.